Assalamualaikum and a very good day. My name is Siti Nabila binti Muhammad Halim from Malaysian Japan International Institute Technology, University of Technology Malaysia, Kuala Lumpur. Today I would like to present my research work entitled Liquid Phase Exfoliated Graphene-MoS2 based Saturable Absorber for Q-switch erbium dot fiber laser. This is my presentation outline for today. Okay, my research background is about the pulse laser technology. Pulse laser technology is the matured and eminent technology that has been used in many applications such as telecommunication, laser surgery, material processing, and many more. Pulse laser operates at high peak power as compared to continuous wave CW, which is operate at average power laser. Q-switch and mode locking is the technique to generate short pulse fiber laser, which can be achieved using active or passive approach. In passively pulsed fiber laser, absorbing material called as Saturable absorber (SA) turns the continuous wave to a train of pulses. The characteristic of suitable SA's material includes low optical loss, tunable energy bandgap, broadband wavelength range, strong nonlinear optical properties, and ease of integration into optical system. The evolution of the base material for SA starts with dyes, sesame, quantum dots, carbon nanotube, until the discovery of 2D graphene in 2004. There has been many ventures into other 2D materials such as topological insulator, TI, black phosphorus, BP, transition metal dicalcigenide, TMBC, enzymes, and many more. And they have shown successful numerous reports that use the material as the base material for SA. As listed here is few properties of the materials, and the materials of choice for this research work is Graphene-MoS2 nanocomposite. The material is one of the recent base material which shows a great demand for to be based as a material for laser generation. Okay, this is among of the few synthesis methods for materials based SA from the literature, such as mechanical exfoliation, chemical vapor deposition, CVD, arc discharge, superacid dissolution, electrochemical exfoliation, liquid phase exfoliation, and many more. Among of the synthesis method, liquid phase exfoliation method is favorable due to its simplicity, low cost production, and scalable production, while still maintaining performance and its ability to synthesis the material for SA. Host polymer is needed to form a physically consistent SA film for ease of integration and removal of SA into laser cavity. And in this research, we introduced natural biopolymer as a non-toxic alternative to the conventional polymer such as polyvinyl alcohol, PVA, polyethylene oxide, PEO, and many other conventional polymer. So the chitin is showing comparable properties to the other polymer and proven to has the characteristic to become the host polymer for SA, which is high tear resistant upon peeling process, high tensile and mechanical strength, and withstand high intensity beam during pulse laser generation. Figure 1 here show the synthesis work of chitin biopolymer solution as established by Wan Nawawi et al. The chitin is prepared from the oyster mushroom. The oyster mushroom will be blended for 5 minutes to increase the surface area, and then it undergo 30 minutes of hot water extraction to eliminate any water soluble elements, followed by the alkaline deproteinization for removing proteins, lipids, and alkali soluble. Finally, it is ready as a chitin solution. Okay. For methodology, Graphene-MoS2 is prepared through liquid phase exfoliation LPE process. As shown in this figure 2, The starting material is normally in the form of the bulk crystal. We disperse it in the suitable solvents for ultrasonication. So the sonication process allows us exfoliation of bulk crystals into nanosheet, and the process involves the weakening of van der Waals interaction inside the material due to the production of microjets and shock waves from collapsing cavitation bubbles. And figure 3 shows the schematic diagram for fabrication of Graphene-MoS2 chitin based SA film through the LPE. Here is more detail on the starting material for graphene and MoS2 solution. We use conductive graphene filament, which will be extruded through 3D printer nozzles, and we mix it with dilute in the tetrahydrofuran THF solution and undergo ultrasonication until the solution disperse homogeneously to become the graphene filament solution. For MoS2, we use MoS2 powder purchased from the cinema Aldrich, and without any further purification, we mix it with THF solution also using the magnetic swirl, and finally got the MoS2 solution. All of this is done under room temperature. Okay, this is the workflow for fabrication of graphene MoS2 chitin as a film. We use 2.5 milliliter of graphene MoS2 solution and mix with the 2.5 milliliter of chitin polymer solution, and ultrasonic in the ultrasonic bath, sonicate in the ultrasonic bath for 60 minutes in the room temperature, and dry in the petri dish for 36 hours at room temperature. And then lastly, we got the freestanding graphene MoS2 SL film. Okay, this is the experimental setup of the Q-switch laser in a abrasive dot fiber laser ring cavity. So we sandwich the SA in the fiber barrel here. Okay. The result from the graphene MoS2 chitin SA based material, we got 1558 nanometer wavelength of optical spectrum analyzer at the maximum input pump power, and the graphene MoS2 chitin based SF film able to generate Q switching pulse pump power from 66.32 milliwatt to 104.93 milliwatt input pump power. So figure 9 shows the graph of pulse trend. The graph indicates a highly stable Q switching operation with little to no amplitude modulation can be observed. Okay, this figure show the repetition rate and pulse width and the peak power and pulse energy. So this is basically typical trend for Q switch operation. We got a high repetition rate at 63.29 kHz and low pulse width at 6 microseconds. And the pulse energy and peak power also shows an increasing trend with increasing pump power. Next is the radio frequency spectrum analyzer, RFSA. It record value of over 60 dB, which is surpass 30 dB, which indicates a good stability parameter of pulse laser. As a conclusion, SA films of proposed material, which is graphene MoS2 chitin, is successfully fabricated by liquid phase exfoliation method in undesirable conditions such as scalable production, low cost consumption, room temperature condition, minimal apparatus, and eco-friendly approach with chitin as the biopolymer. And lastly, passively Q-switch EDFL is successfully demonstrated by using this SA with high repetition rate, low pulse width, good stability, and good repeatability. This is the list of references, and with that, thank you for listening.